This is ELC 131, Circuit Analysis 1, and this presentation is on inductor circuits with DC and pulse sources. Now, the first thing we need to define is the time constant of RL circuits. The Greek letter ta is the symbol for time constant. And the time constant is measured in seconds. One time constant is the period through which the current through an inductor changes by 63%. For RL circuits, mathematically, ta equals L divided by R. So for the circuit of figure 1, the time constant, ta, equals 1 Henry divided by 10 ohms, which equals 100 milliseconds. In this, look at the circuit of figure 1. Figure 1 shows a 10 volt DC source connected to a single pole double throw switch, and the common terminal is connected to a series combination of R1 and L1. Now, when the switch is placed in position 1, current flows through the resistor and the inductor. And this sudden increase in current that occurs when the switch is placed in position 1 causes the magnetic field in the inductor to expand rapidly. And as the magnetic field expands, there's relative motion between flux and a conductor, and this induces a voltage in the inductor that opposes the increase in current. So the instant the switch is placed in position 1, this rapidly expanding magnetic field induces a voltage that keeps the current at 0 amps. Now, as current slows its increase, or slows the rate of increase, then the magnetic field expands more slowly. Therefore, the induced voltage reduces, and subsequently the current increases. And at some point in time, the magnetic field has expanded to as large as it can be, and at that point we no longer induce a voltage that opposes the current, and the current reaches its maximum value, which is 1 amp. Now, while we're here, let's take a look at the polarity of the voltage dropped across R1, which again is due to I times R1, and also note the polarity of the voltage across the inductor. And note that the voltage across the inductor is positive to negative, as shown, and this polarity shows us that the induced voltage opposes the source voltage Vs. Now again, the time constant is defined as the period through which current changes by 63%. And for the circuit of figure 1, the time constant is 100 milliseconds. So in figure 2, we see a plot of the inductor current as a function of time. Now at one time constant, 100 milliseconds, right here, the current has increased by 63%, reached a value of 630 milliamps. Now at 200 milliseconds, 2 time constants, the current has increased 63%, but notice it has increased to 860 milliamps. Again, from 100 milliseconds to 200 milliseconds, the current has increased by 63%, but it's mathematically 63% of 370 milliamps, which is the difference between 630 milliamps and the maximum current of 1 amp. At 300 milliseconds, the current has increased to 950 milliamps. And at 400 milliseconds, the current has increased to 950 milliamps, 980 milliamps. And at 500 milliseconds, 5 time constants, the current has increased to 993 milliamps. Now, the current will never reach 1 amp because during each time constant, the current increases by 63%. So the current can never mathematically reach 1 amp. However, we assume that after 5 time constants, the current has, for all practical purposes, reached its maximum value of 1 amp. Now, figure 3 shows us the voltage dropped across the resistor as a function of time. And again, the voltage across the resistor equals I times R1. So at time 0, the voltage across R1 is 0 volts because again the induced voltage keeps the current at 0 amps at the instant the switch is placed in position 1. At 100 milliseconds, the voltage across the resistor has increased to 6.3 volts. At 200 milliseconds, the voltage across the resistor has increased to 8.6 volts. At 300 milliseconds, 9.5 volts. 400 milliseconds, 9.8 volts. And at 500 milliseconds, 5 time constants, we assume the voltage across the resistor has reached 10 volts. And again, if you look back at the plot shown in figure 2 of current, we see that VR1 and I have the same curve, again, because VR1 equals I times R1. Now, in figure 4, we see a plot of the inductor voltage as a function of time. And mathematically, VL equals V source minus VR1. So at time 0, the instant the switch is placed in position 1, the voltage across the inductor is 10 volts. Again, the induced voltage at that instant keeps the current at 0. So VL has to equal VS. At 100 milliseconds, the inductor voltage has dropped to 3.7 volts. 200 milliseconds, it's dropped to 1.4 volts. 300 milliseconds, it has dropped to 0.5 volts. At 400 milliseconds, the voltage has dropped to 0.2 volts. And at 500 milliseconds, 5 time constants, we assume that the inductor voltage is 0, that the magnetic field has expanded to as large as it can be, and there is no more induced voltage. Now, let's look at the circuit of figure 5. The single pole double throw switch is placed in position 2, and this interrupts the current supplied by the source. And what will happen is that the magnetic field will collapse since there's no more current from the source that's creating this magnetic field. And as the magnetic field collapses, we have relative motion between flux and a conductor, and this relative motion induces a voltage that opposes the change in current. So the rapidly collapsing magnetic field will induce a voltage that attempts to keep 1 amp of current flowing through the inductor. And now with the switch in position 2, this is our path for current. So this collapsing magnetic field is now the source of energy for the voltage that keeps current flowing. So again, the instant the switch is placed in position 2, an induced voltage is created, or a voltage is induced, that keeps 1 amp of current flowing. Now, as the current decreases, the rate of collapse of the magnetic field will decrease, the induced voltage will decrease, and at some point in time, the magnetic field in the inductor has collapsed completely. There will be no more induced voltage, and there will be no current flowing in the circuit. Again, one time constant is the period through which the current through the inductor changes by 63%. So the instant the switch is placed in position 2, there will be 10 volts, or excuse me, the induced voltage will keep 1 amp of current flowing. But after one time constant, 100 milliseconds, that current will have reduced to 370 milliamps. That's a reduction of 63%. At 200 milliseconds, the current will have reduced to 140 milliamps. At 300 milliseconds, 3 time constants, the current will have reduced to 52 milliamps. At 4 time constants, 19 milliamps. And at 5 time constants, the current will have reduced to 7 milliamps. Again, the current will never reach 0 because during each time constant it reduces by 63%. However, at 5 time constants, we assume the magnetic field has collapsed completely and the current flow through the inductor is 0 amps. So in figure 7, we look at the voltage across the resistor as a function of time. And again, VR1 equals I times R1. So using the current values from the previous slide, we see that at time 0, the instant the switch is placed in position 2, the resistor voltage is 10 volts. One time constant later, the resistor voltage has reduced to 3.7 volts. At 2 time constants, it is reduced to 1.4 volts. At 3 time constants, it's reduced to 0.5 volts. At 4 time constants, 0.2 volts. And again, we assume that at 5 time constants, the resistor voltage has reduced to 0. Now in figure 8, we look at a plot of the inductor voltage as a function of time. Now, if you look back at figure 5, it shows us the circuit with the switch in position 2. Note the polarity of the inductor voltage is negative to positive with respect to ground. Again, in order to keep current flowing, the inductor voltage has to change its polarity from positive to negative to positive. The inductor voltage is the source for current when the switch is in position 2. So at time 0, the instant the switch is placed in position 2, the inductor voltage is negative 10 volts. And as time passes, that inductor voltage gets smaller because, of course, the current gets smaller as time moves forward. So at 1 time constant, we're at negative 3.7, 2 time constants, negative 1.4, negative 0.5, negative 0.2, and at 5 time constants, again, we assume the inductor voltage is 0. Now, before we look at the next section, we need to discuss or define E. And E is actually referred to as Euler's number. And E is just a number, kind of like pi. E equals 2.7818281828. It goes on and on, just like pi. And of course, you remember pi describes the mathematical relationship between the circumference of a circle and the radius, and the area of a circle and the radius. E describes the rate at which things increase or decrease in nature, such as population increase or decrease, radioactive decay, actually the interest on your savings when you put money in the bank, and other quantities such as the R value of insulation as a function of adding additional inches of insulation. But E also describes the rate at which current increases and decreases in an inductor. Now, don't confuse E on your calculator with EE. Remember, EE is how we multiply a value times 10 raised to some number. On your TI-30X Pro calculator, the E key is shown, E raised to some power. Again, depending upon the calculator you have, this may be shown on your keypad as E to the X power as shown. Now, in the previous examples we looked at for a capacitor for an inductor energizing, we had a method to calculate I, VR, and VL only at integer time constants. 1 time constant, 2 time constants, 3, 4, 5. However, there's a lot of situations where we need to calculate circuit quantities at times other than integral time constants. So the equation shown allows us to calculate the current flow through an inductor at any time, and that is that I, and note again this is a lowercase I, which means it is an instantaneous value, equals I max times 1 minus e to the negative t over tau power, where t is the time we wish to calculate the current at, and of course tau is L divided by R. And the maximum current, of course, is Vs divided by R total. Now, we know that V equals I times R, so VR, again, note this is an instantaneous quantity, can be calculated using Ohm's law, I times R, or we can use the equation shown to calculate the voltage across the resistor as a function of time. And again, this equation assumes that the current is 0 at the beginning of the energizing period. Now we can use Kirchhoff's voltage law to calculate the voltage across the inductor, VL equals Vs minus VR, or we can use the equation shown to calculate the inductor voltage. Again, this is an instantaneous quantity. The inductor voltage equals V source times e to the negative t over tau. Again, we have to assume that the current through the inductor is 0 at the beginning of the energizing period. Now, during the de-energizing period, we can calculate the current through the inductor with the equation shown, I equals I final times e raised to the negative t over tau power. Again, instantaneous value for current. And VR equals I times R, Ohm's law, or we can use the equation VR equals I final times RT times e to the negative t over tau power. And during the energizing period, the inductor voltage equals negative VR, or VL equals negative I final times RT times e to the negative t over tau power. So these equations allow us to calculate the inductor current, the resistor voltage, the inductor voltage as a function of time during the energizing and de-energizing periods. Now, in the previous examples, we looked at the operation of this circuit containing resistors and inductors with a DC source. And here we look at the operation of a similar circuit with a DC pulse source. So referring to the circuit of figure 9, note that the source voltage is a pulse waveform. It goes from 0 volts to 10 volts. It stays at 10 volts for 500 milliseconds. Then it goes to 0 volts, and at 1 second it would go back positive again. So this is simply a square wave that's raised up to a DC level from 0 volts to 10 volts. Now you note the time constant of the circuit of figure 9 is 500 milliseconds, and the pulse period is the time constant of the circuit of figure 9 is 100 milliseconds. The pulse period is 500 milliseconds. So during the energizing period, the current reaches the maximum value of 1 amp. And during the de-energizing period, we assume that the current reaches 0. So we see the current increase exponentially from 0 to 1 amp and decrease exponentially from 1 amp back to 0. And looking in figure 12, we see a plot of the inductor voltage as a function of time. And the instant at the start of the positive pulse, the inductor voltage is positive 10 volts, and it decreases to 0 over a period of 5 time constants. The instant that the pulse source goes to 0 volts, a voltage is induced to try to keep 1 amp of current flowing. So the inductor voltage here is negative 10 volts, and through a period of 5 time constants, the inductor voltage drops or goes to 0 volts. Now let's look at an application of inductors in DC circuits. So referring to the circuit of figure 13, we see a 5 volt DC source and a 100 millihenry inductor connected in series with a 1 k ohm load resistor. And what can happen in a circuit like this is because of things like lightning strikes, motors turning on or off, welding equipment nearby to our circuit can cause voltage spikes and voltage drops or voltage sags on this DC voltage. So we see that at 100 milliseconds, we see a 5 volt spike occurring on the source voltage. And again, this spike could be from a lot of different sources. And what happens is that this voltage spike causes an increase in current through the circuit, and that increase in current causes a rapidly expanding magnetic field which induces a voltage that opposes that increase in current. So therefore the voltage across the load is only going to increase a small amount as the source voltage increases by 5 volts. And then on the positive transition of this voltage spike on Vs, we see a an induced voltage in the inductor that opposes that decrease in current. And what the inductor does is smooth out that voltage spike as shown. So a 5-volt spike on voltage only causes approximately a 0.5 volt increase in the load voltage. And similarly, we can have a voltage sag, and this could be simply a temporary drop in the source voltage coming in on the line. And again, when the current goes, when the source voltage goes from 5 volts down to 0 volts, the current is going to try to decrease rapidly. And that decreasing current will cause the magnetic field in the inductor to collapse, inducing a voltage which will have a polarity of negative to positive and somewhat smooth out the sag or drop in the source voltage. Then, of course, when the voltage spike or the voltage sag goes from 0 volts back up to 5 volts, the magnetic field will expand rapidly. This will induce a voltage that actually has the opposite polarity and smooth out this source voltage or the voltage supplied to the load. So a drop of 5 volts in the source voltage results in only a drop in load voltage of about 0.5 volts. And of course, this is important if this load over here represented a programmable device such as an Arduino or another programmable system, because if we apply too much voltage to this load, it could damage or destroy the load. And of course, if the voltage drops down too far, it could cause the digital system to reset, which is generally not a desired outcome. So with this presentation, we looked at the operation of inductor resistive circuits, LR circuits, with a DC voltage, where we energize and de-energize the inductor and see that the changing magnetic field in the inductor induces a voltage that opposes the change in current. We looked at the operation of these LR circuits with a pulse source and saw that applying a DC pulse waveform to an LR circuit results in an exponential increase and decrease in current. And we finally look at the application of inductors in DC circuits to smooth out voltage spikes and voltage sags.